Hey everyone. Today we're going to do an interesting practice problem where we are going to try and find the two missing elements in some sequence of numbers. So what we're going to do is we're going to take in an array, and this is going to be an array of all the numbers from 1 to n in some random order, except that two numbers from that array, two numbers from that sequence are not included in the array, and so our job is to figure out what those two missing numbers are. So as you can see in this example, we have the sequence from 1 to 4, but since we're missing two numbers and we're going to say that we're going to start at 1, we're missing the number 1 and we're missing the number 5. So hopefully that makes sense, and we're going to just go ahead and dive right into this problem. And the first thing we want to do is make sure that we understand the question. So for example, is 0 a number in the sequence or not? Does this sequence start at 1 or does it start at 0? Because that's going to affect this problem. That affects, as I just mentioned in this example, which are the two missing numbers? Is 0 the first missing number or is 1 the first missing number? And since we are starting from 1, that means that we're missing the number 5 versus missing 0 and 1. So you want to make sure that you really understand what is being asked of you. And we might also check whether these are going to be integers or longs, because that might affect the size of the input. For example, if we have integers, we know that there is a fixed maximum size of this array that we could have, right? Because they're only all the positive integer values, or all the unsigned integer values, I guess. But if we have longs, then that makes this much bigger, and that may affect how we decide we want to solve this problem. So let's actually now discuss how we might approach this problem. And a couple things come to mind at first, but what I'm going to do for this problem is actually start with a simpler problem. Because we're trying to do a lot of things at once here. We're trying to figure out which numbers are missing. We're trying to do it efficiently. We're trying to not take up too much space, all these things, and that's going to make it difficult. So what I'm going to do is I'm going to start by solving a subset or a slightly different problem, which is the problem of we're only missing one number from the array. And so how would we do it in this example? So we have like 1, 2, 4, 5, and we're missing one number. So the result would be 3. And so how would we solve this problem? And there are a couple of approaches we could take. So first of all, we could create a Boolean array, or some sort of array that would keep track of all the values that we've seen thus far, and we could traverse through our list and sort of tick off the ones that we've seen, and then once we get to the end, we would have one value left over that we hadn't seen. So we would just, in this case, we would take the length of the array, which is 4, and so we know that we're looking for a sequence of 5 elements, or all the numbers from 1 to 5, and we would go through and we would basically create a Boolean array of length 5 and check off from 1 to 5 and set the value to be true, right, of all the elements from 1 to 5 that we see in the array. So if we were to do this, the time complexity would be O of n, right? Because we're going to have to traverse the array once, and then we're going to have to traverse our Boolean array once to find the one that is unmarked. And then also space complexity would be O of n. So that's not bad. That's like a decent algorithm, although we are using a decent amount of time and space. Especially the space may be an issue if we have a really large array. So that might be something that we'd want to think about. Another approach we could take, so this is the approach of using a Boolean array. Another thing we could do is just sort our array and check for anywhere where there is an item out of sequence. So we would sort the array, and then we would traverse the array, and this array is already sorted, so you can see in this example, we would say for each item, is the previous item one less than it, or is the next item one more than it? And if we get to here, we say that, oh, the next item should be 3, but it's actually 4. And so we know that there's a gap in our list there, and so we would know that that was the correct number, and we could return the number that way. And of course, sorting takes O of n log n time. So that would be O of n log n. But we don't have to use any additional space. We're not going to have to create a new array, and we're not going to have to do anything. So the space, the additional space, is going to be O of, it's going to be constant, right? Because that, and so that's the advantage. And as you can see, by using more time, we have this trade-off. So we can do it in less time by using more space, or vice versa. And the other slight disadvantage to this solution of sorting is that we're not going to end up with the, we're going to end up modifying the input array, which may not be a good thing. So you'd want to check with your interview about that. And we could get around that by copying our array and then sorting it, but then we end up using O of n space, so we'd be better going with this solution. But we can actually do better than this. And we can do better than this by taking advantage of the fact that we know the sequence that we know what the sequence is. And we're only trying to find the difference between the existing sequence and the sequence and the like ideal sequence. So what we basically have, so the quote unquote ideal sequence, or the correct sequence, would be this. But maybe in some random order. And the sequence that we actually have is this. So we can look at the properties of our two lists and basically compare them. So for example, we could sum up both arrays and look at the difference of those two sums. Because when we sum up this array, we're going to get the sum of this whole thing. And then when we sum up this array, we're going to get the same sum, but -3, right? Because we don't have a 3 in here. And so we're going to sum it up, and then we're going to get the, and then we could sum up basically this ideal array, and then we could sum up the one that we have and take the difference of them. And the difference is going to be that one element that's missing. And so that's really the technique that is going to be the most efficient for us, because by doing the sum, we can take, or by doing some sort of combination of all the numbers, we can do that in constant space, but it's also going to only take linear time because it just has to take the sum. And then we can do one better by actually doing an XOR instead of the sum. Because what happens is, as hopefully you know, x XOR x equals 0. So when you XOR a number with itself, it zeroes out. And XOR is also associative and commutative, and it has all those properties that mean that if you have x XOR y XOR x, you end up with getting y back. And that's going to be the property that's going to be the most useful to us, because let's say that we XORed all these numbers together and then XORed all these numbers with that original one. The 1s cancel out, the 2s cancel out, the 4s cancel out, and the 5s cancel out. And so then we're left with 4 left over. And the advantage of the XOR is that, unlike addition, it's not going to take up additional space. Because with the addition, we might have to worry about overflow, right? Because we're going to be adding all these numbers together. So if you have a lot of numbers, you might end up getting a really large sum that would overflow your integer. So you'd need to have a long, or if you had an array of longs, you might need to use some sort of like Java big integer or something like that to actually store the value. But by using XOR, we're never going to use more bytes or more bits than the maximum value in our set. So if this was an array of integers, we would never use more than 32 bits. And if it was an array of longs, we've never used more than 64 bits for our XOR. And so that's the great thing about XOR, and we'll always get back the right value. So hopefully you see now how we can implement this code. So we can implement we can get the missing value for where it's missing a single value. We can just write a simple function that's going to do this. So it's going to return an int, and I'm going to call it one missing for lack of a better name. And it's going to take in an array of integers. And I'm going to do this, I'm going to create temporary variables for different things, but in theory you could do this all with a single variable. But this is just going to make it a little bit more clear what's going on. So we're going to call it total XOR equals 0, and int r XOR equals 0. And so total XOR is going to be the XOR of the whole sequence, and R XOR is going to be the XOR. So total XOR would be the XOR of this, and R XOR is going to be the XOR of this. And then by XORing those two together, they're all going to cancel out, and we're going to end up with our 4 at the end, or our 3 at the end. So all we have to do is just do a for loop for each. So for int I equals 1, I is less than or equal to r dot length I length plus 1 and I plus plus, we get total XOR equals I. And so what we're doing is we're going from, we're using the property that our sequence starts at 1 and not 0. So even though our array indexing normally starts at 0, we're going to have to start 1 up. So we're basically going from 1 to the length of the array plus 1 inclusive. So the length of the array is going to be, in this case, the length of this array would be 5, and then we're going to go from, this should actually be less than, right? So we're going to go from I equals 1 to we're actually, sorry, no, this should be right, because our array is this. So our array is actually missing one element. And so we want to go from, so we have an array of length 4, and we want to go from 1 to 5 inclusive, right? So we do the length of the array plus 1, and then we do this less than or equals rather than a normal less than that we would do. So we have this, and then we're going to do for int I in R XOR is going to be XOR equal to I. So what we just did is we're getting the total XOR, and then we're getting the array XOR like this, and then all we have to do is return total XOR XORed with R XOR. So I'm not going to go through and test this code because it's fairly straightforward, but I would encourage you to do that on your own. And so hopefully this makes sense so far. And now let's return to our original problem. So I'm going to delete this, but you can remember how that code works. And now what we want to do is we can actually use that solution to the single problem to solve this missing 2 problem. So where we're missing 2 elements. So for example, like this would then return 3 and 5. So how can we do this? Well, we know a couple properties of this already, right? So what we could do is we could use a similar technique to before to compute what the value is of 3 XOR 5. Right, because we could XOR this array, we could XOR this array, and then XOR them together, and we could get the XOR of 3 and 5, which is fine, but that's not really going to help us because we're not going to be able to retrieve either of those individual values from the XOR, right? Because we need to know one of them to be able to retrieve the other. And we could also get the sum of 3 and 5 because we could sum up this one and sum up this one and subtract them. And that's actually not going to be helpful on its own either, but what we can do is we can combine the two. And so what we know about the sum, and we can do it with addition only, but I'm going to use combine the two to make it work slightly better. But what's going to be crucial here is 2 properties. One is we know that both values are unique. Right, so we know that we're not missing like 2 5s out of the array or something, because that would not be part of the sequence. And the other thing we know is that the value of each item has to be either greater than or less. So one of them has to be. So basically, we know that 3 plus 5 is 8. So we get back this. We would have this value 8, and we're trying to return 3 and 5. And what we know is we can split this in half and say that one of these values is, by definition, less than 4, and the other is greater than 4. One of them has to be less than this value, and one less than half of that value, and one of them has to be greater than half that value. Because if both of them were less and both of them were greater, then obviously we wouldn't have that result as our sum of two numbers. And also, they can't both be 4. So what we can do is we can divide this array in half and do what we did for the single, to find a single missing number on each half separately, right? So what we can do is we can say we get the sum, and then what's half of the sum? So half of the sum is 4. And we can say, okay, let's XOR all of the numbers. Let's XOR all of the numbers from 1 to 4. And then we're going to XOR all of the numbers in this array that are less than 4, less than or equal to 4. And then we're going to XOR all the numbers that are greater than or equal to 4. And so what we're going to end up with here is we're going to end up breaking this down. So we're going to XOR, we're going to do 1 XOR 2, XOR 3, XOR 4. And that's going to be XORed with 1 XOR 2, XOR 4. And then we're going to have, so that's going to be the first half. And then we're going to end up with 5, just XORed with itself, or 5 XOR 0, which is 5. And that's going to be XORed with 0 because we have no numbers greater than. So what you can see here is that we're going to search in the first half, and then we're going to search in the second half. And we can look at it. Let's look at another example that might be slightly more clear, because this isn't divided very evenly. So if we look at an example like 1, 2, 5, 6. So we're missing 3 and 4. So 3 and 4. And we can get rid of this. Then what we're going to do is we're going to have our actual sequence should be 1, 2, 3, 4, 5, 6. And we're going to get the sum is going to be equal to 3 plus 4, which is equal to 7. And now what we're going to do is we're going to XOR the two halves of each array. So we're going to say, what's half of 7 is going to be 3, because we're just doing integer division here. And so we're going to say XOR the sequence up to 3. So 1 XOR 2 XOR 3. And then we're going to XOR it with all the numbers in this sequence that are less than or equal to 3. So we're going to XOR it with 1 XOR 2. And then that's going to be equal to 3. Now we do the same thing again. We XOR 4, 5, and 6. And then we XOR that with 5 and 6. And that's going to, obviously, again, they cancel out. The 5 and 6 cancel out. So we return 4. And that's how we're going to do this. And this way, we're going to do it in linear time, and we're going to do it using constant space, which is the cool thing. So let's actually code this up. Hopefully that makes sense. And if not, you can leave a comment on the blog or in the YouTube video, and I will be happy to respond to that and help you through the problem. But let's go ahead and implement this. So we're going to say it's going to return. I'm just going to return an array of array of length 2. That is going to be our array of integers, and I'm going to call it 2 missing to go along with our theme of naming these functions. And it's going to take in an int array called r. Now, and again, I should have mentioned this earlier, but I'm going to assume that the array is properly formatted. Or in other words, I'm going to assume that we're getting in an array that has exactly 2 missing integers. Because otherwise, that's not really going to... There's no way for us to easily check that the input is correct, because it's going to... The only way that we could do that is... we could validate our result after we get it, but there's no way for us to sort of pre-check that the result is, or that the input is valid very easily. So I'm just not going to worry about it. And so first what we need to do is we need to take the sum, right? Because we need to find what half of the sum is. And for doing this, I am a little bit worried about overflow, as I mentioned earlier, but I'm just going to, again, making some assumptions here. I'm going to assume that by using a long to store the sum, that's going to be big enough to store any possible sum. that we could get from our integers. And I'm just not going to worry about it more than that. So total sum is going to be equal to 0, and long R sum is going to be equal to 0. And then we're doing basically the same thing as we did before. So we can either iterate through the numbers from 1 to r.length plus 2 and add them all together, or if you remember your math from a while back, from middle school or something, you'll remember that the sum of the numbers from 1 to n is equal to n times n minus 1 over 2. So if you don't remember that, it's not a big deal, but that's just slightly simpler. So I can actually, rather than doing this, just put it's going to be r.length plus 2. So I'm actually going to create a variable here called size, which is going to be r.length plus 2. And then we get that this is going to be equal to size times size minus 1 divided by 2, just so that we don't have to iterate through the whole thing. We're going to obviously get the same result. And then for this r sum, I do have to iterate through, so I'm going to say for int I and r sum plus equals I. Just like that. And then we need to have this value, right? We need to get what I'm going to call it the pivot value, because it's basically it's sort of like a pivot in quicksort, or it's like the center point. So I'm just going to say that int pivot, and we know that the pivot's going to be an integer, right? Because the pivot is within this sequence. So instead of a long, even though I have these are both longs, the pivot is going to be within the range of the integers. So I'm going to say pivot is going to be equal to, I'm going to cast it to an int, and then I'm going to do total sum minus r sum divided by 2. Right, so the pivot is just the middle point. And since they are both longs, I'm going to cast it to an integer. And then I need to do all these XORs. So again, I could do the XORs all sort of in one variable and just keep XORing stuff, but I think that's a little less clear. So I'm all for adding extra variables if it's going to clarify your code. And so as a result, I'm going to do int total left XOR and total right XOR. So total left XOR is going to be the XOR from 1 to pivot, and right XOR is going to be the XOR from pivot plus 1 to size. And so it's just like the left and right subarrays. So I'm going to have them all equal to 0, and then I'm also going to have the int r left XOR equals 0, and then same for the right. So int total right XOR equals 0, and int r right XOR equals 0. And then I need to go through and XOR them all. So I can say for int I equals 1, I is less than or equal to pivot, and I plus plus, I'm going to XOR them into total left XOR. So total left XOR equals I. And then I'm going to do the same thing for the right side. So I'm going to say for int I equals, and in this case, it needs to be pivot plus 1. And I is less than or equal to size, I plus plus. It's going to be total right XOR equals I. Like that. And then finally, I'm going to XOR the actual values in the array. And so I'm just going to do one pass through this and XOR to one or to either R left XOR or R right XOR depending on the value. So I'm just going to say for int I in R, we're going to XOR if it's less than or equal to pivot, we're going to XOR to R left XOR, and otherwise we're going to XOR to R right XOR. So I'm just going to say if I is less than or equal to pivot, R left XOR equals I, and else our right XOR equals I. So that's that, and then all we have to do is just make our array and return it, because this is all we have to do is XOR these together and XOR these together as we did here to get our output. And therefore we are going to return a new int array, and the values are going to be total left XOR R left XOR and total right XOR R right XOR. And that's all there is. So it's a pretty neat solution, I think, to a problem that can be solved less efficiently, but this is just I think it makes a lot of sense once you've figured out how to do it. It could be a hard solution to come up with in an interview, but I think it's a really neat solution, and we can just quickly go through an example to see how we can just quickly go through this example. So we're going to say int size is, so size equals 6, right? Because we have this array of length 4 plus 2. Total sum equals, let's see, it's size times size minus 1. So 6 times 5 divided by 2, which equals 30. And so we get, let's see, 15. And so we get 5 times 6, or 5 plus 6 plus 4 is 15. So, whoops, actually this should be plus, right? Because the formula should be n times n plus 1 divided by 2. So what we actually get is n times n plus 1, so 6 times 7 divided by 2, which is equal to 42 divided by 2 is 21. And if we sum this up now, we get 10 plus 5 is 15, plus 6 is going to be 21. Yeah, so that's right. And then we are going to calculate our array sum. So let me just get rid of this. So array sum is going to be the sum of all of these, which is going to be 5 plus 6 plus 2 plus 1. So we get 3 plus 5 is 8, plus 6 is 14. So our sum equals 14. And then we get that the pivot is going to be equal to the difference of those divided by 2. So the difference of 21 and 14 is going to be 7, right? So we get pivot equals 7 divided by 2, which is, again, we're going to do integer division. So it's going to be 7 divided by 2, which equals, in this case, 3. And then we're going to do all these XORs. So we don't need these anymore. And so we get that I'm actually not going to try and compute all these XORs in my head, because that is going to be a pain in the butt. So I'm just going to write them out so that we can then cancel things. So we're going to get the total left XOR is going to be equal to the XOR from I to pivot, so from 1 to pivot. So that, and pivot is 3, so it's 1 XOR 2 XOR 3. And our left XOR is going to be 1 XOR 2, because, well, actually, let's do this in the proper order. So total right XOR is going to be equal to pivot plus 1, which is 4, to size, which is 6. So 4 XOR 5 XOR 6. And then we get our left XOR and our right XOR. And so we go through these, and each time we check whether it's less than or equal to pivot. So 1 is less than or equal to 3, as is 2. And then the other two are greater than 3, so 5 and 6. Then we are going to come out here and we're just going to XOR them together, right? So we're going to XOR this with left XOR. So we're going to say that we end up with this array that is 1 XOR 2 XOR 3 XOR 1 XOR 2, and we get 4 XOR 5 XOR 6 XOR 5 XOR 6. And if you cancel these, the 1s cancel, the 2s cancel. So we're left with 3. And in this case, the 5s and 6s cancel. So we're left with 4. And that's the result that we want. So hopefully that makes sense. Let me know if you have any questions below. In terms of runtime for this, we're going to iterate through the whole array once to get the sum, and then we have to iterate through it a couple more times for this stuff. So the runtime is but we iterate through it a constant number of times. So we're going to get a runtime of big O of n, which is just a linear runtime, which is good. And then we're going to use space we're going to have this one long, or these two longs that are going to store the sums, and we're going to have these 4 XORs, and those are going to always be the same number. And so the extra space that we use is constant. So our space usage is going to be constant space. And so, yeah, that's all there is to this problem. Hopefully that made sense. Let me know in the comments below or on the blog if you have any questions, and otherwise, I'll see you guys again next week.